Hello everyone, I hope you enjoyed the break. So what I want to talk to you about today is kind of a meandering story, but hopefully it will all come together at the end. This work all started when myself and a colleague of mine, I do machine learning work at Microsoft, and myself and a colleague of mine by the name of Weyoung Tak, got together and we were asked to create a big demo that we could show like on stage at a big Microsoft conference, something like that. And we both do machine learning work. He's a data scientist in the Azure machine learning team. And so the two of us got together and we're like, okay, we have to come up with some cool demo that shows some cool machine learning stuff that Microsoft has done. And we're putting our heads together, and Weyoung got fixated really early on the idea of doing something with drones. I think he just really wanted an excuse to expense a drone, right? So he's like, drones, we gotta do something with drones. And when this work started, this was like about a year plus some ago. And this was, how many of you guys watch Game of Thrones? All right, so this was when the hardcore stuff was going down on the show, right? The Hodor episode had just happened, like Daenerys had just burned down all the cause, like it was wild. People were taking time off work to recover, right? All right, so all this stuff was happening, and so this was totally in my head, and also, much like Weyoung, I was thinking, okay, we want to do drones, we want to do machine learning, we have these amazing, facial recognition APIs and such, and so much like Weyoung, I'm like, okay, here's a great way to be able to expense a really expensive Daenerys Targaryen costume. What if we had the drones be my dragons and I walk on stage and I can get my 3 dragons to follow me? So we're just going nuts with all of these silly ideas for what we could do. But then at some point, reality set in, and the first major decision we had to make was to decide, what kind of drone are we going to buy? And so that's when it's really nice to work at a big company like Microsoft or Google or Amazon would probably be very similar. It's a huge company. There's a lot of people doing work in a lot of different areas. So we started nosing around, asking, is there anyone else doing work with drones and work with machine learning, and what else is going on? And that's when the third person on that slide, Ranveer Chandra, came in to our stuff. So Ranveer works for Microsoft Research, and he is doing some amazing work around using machine learning together with IoT, drones, and some neat networking research to be able to essentially try to solve world hunger. So let me tell you a little bit about that first, and then we'll get back to the Game of Thrones stuff in just a second. All right, so the issue that they're trying to tackle is the idea of we need to increase our rate of food production. So there's some data that was released at the United Nations in 2009. And at this big UN summit, someone made a big presentation that by the year 2050, the world is going to have 9 billion people. And we essentially need to double our current rate of food production to be able to feed all of these people. And so what Ranveer was really looking at is, okay, how can we use technology to improve the yield, the overall yield of food production? So enter the concept of precision agriculture. So I was not familiar with this concept prior to coming into this project, but the idea is that right now, when you're a farmer and you water your fields, typically fields are watered homogeneously, right? You have a big sprinkler and you water every part of the field the exact same amount. However, the idea of precision agriculture is that fields aren't actually uniform. If there's a little, dip in the field or something, then the water's going to run down, and that area is actually watered a little better than, the slope or the top of the runoff. So you can use that information to be able to only water exactly, the parts of the field that you need, and that saves water, and then you can use that information in conjunction with other things to work on increasing yield. And then there's a whole lot of work that's being done in other areas as well around collecting other information to give a better distributed look at the farm. But what I heard from, and so there's an obvious solution to that, right? Any of you guys who are engineers or developers or tinkerers may have played with some IoT stuff and may have seen that it's pretty cheap to get these little moisture sensors in the ground. So okay, that makes sense. You put some moisture sensors in the ground, and then we can use precision irrigation, for example, to only water what needs to be watered. However, what Ranveer told me is that it costs approximately $1,000 per sensor to implement this. And I was like, you sure about that? Can you check your numbers? Because I can just pull up adafruit.com right now, and here's these moisture sensors. They're actually pretty cheap. And it turns out the actual cost of the sensor is negligible. That's not that expensive. So where is this extra money coming from? And it turns out that the next thought I had is, okay, power, right? You need to provide power to these sensors, so maybe that's where the issue is. However, they actually derive power through solar panels. So there's a nice solar panel that can collect the rays of the sun and convert that into energy, and it's not that much, but the little IoT boards don't need that much power to run, so you can actually do it primarily just through a solar panel. And solar panels are maybe $100. I mean, it's not that expensive. It's not $1,000 per sensor. So where is that extra cost coming from? If we have the sensor, the power taken care of, it turns out what is actually contributing to that $1,000 a sensor cost is connectivity. That's the hard part. When you think about, if any of you have ever driven through a more rural area and tried to get cell phone coverage or that sort of thing, you know that the cellular towers are less motivated to provide great coverage in more rural areas. And then if we want to do some of these things in third world countries as well, they don't always have the cellular infrastructure that's there. And then there's other technologies like wireless, but when you're considering like a 1,000-acre farm that some of these farmers have, you would need so many wireless access points to make that happen. So that's another one of the challenges that they were tackling, and I'll talk a little bit more about that later. All right, so where does the machine learning come in, and where do the drones come in? Let's talk about that. So if we can assume for right now that we want to limit the number of sensors that we have available just because of this cost. So what we can do is put a smaller number of sensors throughout the fields, but then use that sensor data in conjunction with aerial imagery from drones, okay? So if we fly over fields and take aerial imagery of drones, then we're going to get information like how green versus how brown things are and kind of what those things look like. And then taking that aerial imagery from drones flying over the farm in conjunction with that sensor data that we're getting from those moisture IoT sensors, we can apply machine learning models to that and extrapolate the value so that we get moisture levels for the entire field, even the ones that don't have sensor coverage. Okay? So that's what we're going to try to dig into a little bit more deeply. So we have these cameras, these drones, these sensors all feeding data. And this is part of a larger project called FarmBeats, where they're trying to give the farmers an all-up look at their farm. So they also feed in things like weather data and things like that, and then can produce various insights, also using machine learning, things like the ideal time to plant, where are the best areas to plant which crops, all kinds of other cool things like that that can improve yield overall. All right, so here's a quick look at the farms, just because these are kind of fun to look at. So Microsoft actually is implementing some of these techniques that we're talking about in a 2,000-acre farm in upstate New York. So again, when you think about connectivity over 2,000 acres, like that's kind of a challenging problem. And then we also have a smaller farm, about 100 acres, so still big, but a 100-acre farm in Carnation, Washington, which is very close to where Microsoft's main headquarters is in the Redmond area, which is a suburb of Seattle. And so if you take a look at what you can do with these drones now, we have the drones kind of flying overhead, and I can show you a quick little animation of this. And so this is the drone flying over this farmland, and then these are the pictures that the drone is taking at each of the red dots, at each of the positions there. So right here you can see it's about to make a turn, and you'll be able to see that, woo, see how the landscape is turning as it makes this little turn right here. Cool. So obviously if we're taking pictures every so often, then on the back end you can stitch that all together and get a nice all-up view of what the farm actually looks like. All right, then the next thing to think about is sensor placement. So we can actually use machine learning as well to determine where can we best place those sensors to be able to extrapolate the data the best. And so there's a lot of neat things you can do with kind of the aerial imagery like this. One of the things is weed detection. So thinking about just when you have aerial imagery like that, can you see like where weeds are popping up? If you're dealing with a 2,000-acre farm, just managing all of that can be overwhelming. So knowing where are the weeds coming up and what areas are best to let the cattle graze, right? Like in this area, it's, it's still very green and there's a lot of grass available. In this area, they've eaten most of it, like that sort of thing. So just knowing, too, where to put your herds is another really cool thing you can do with this aerial imagery. But we can use this to place the sensors in the most optimal positions to be able to extrapolate data. So maybe one right here, kind of in that green area, maybe one over there, and one near the edge where that little water line is, and then be able to use that to extrapolate across the whole field. All right, and here's what the sensors actually look like on the ground. So we have a little board here, and we have it enclosed in a waterproof casing, since these things are living outside. So it's in a waterproof case, but the little sensors, the measuring, the things that can measure moisture are, stick out of the waterproof case, and those actually get embedded in the dirt. And then we measure at 2 different levels. I think it's like 4 inches under and 12 inches under, so you get 2 different moisture levels on how deep and how much moisture there is. And then you can see the little solar panel at the top, and then that reads and provides power and charges it as well. And then there's actually a little infrared camera on here as well, so you can get imagery of kind of the surrounding area and just see what it looks like. It's really cool, too, for measuring things like the spread of pests and other things. But you can see, all right, in this area, these things look like they're dying a little bit. And even with the infrared camera, you can see that at night as well. All right, so here's where some of the machine learning comes in. So we're actually using Gaussian processes to do this, because you can assume a nice, normal distribution. And there's really 2 kind of things we're trying to balance here. So one thing is the spatial smoothness factor. So since we're measuring like the soil and kind of what that environment looks like, if there's things that are nearby, so here's this green area, another green area right next to it, like those things are probably going to have similar readings. They've probably been watered the same amount similarly. So you can assume some stuff through proximity, right? And then secondly, areas that look similar should have similar sensor values. So if we have 2 patches of area that are both kind of the same shade of darkness, that have both been watered recently, if they're kind of the same shade of darkness, there's some assumptions that you can make around, okay, they probably have a similar amount of moisture, like that sort of thing. So there's neat things we can do to tie those together as well. All right, and then to put that all together, we have now our sensor data that are coming from those things that you saw, the IoT, the little board. That's getting sent to the cloud, and then you can use that together with the data from the drone. And I'll talk a little bit more about the drone data in a second, but we actually send a drone up, fly it over that farmland, and then we don't stream it in real time. We just collect all the data like on the drone, so it's storage on like a USB drive, portable storage that's on the drone, and then we bring it back down and then stitch together the imagery after that. But what it can give you then is this great spatiotemporal view of the farm. So we can measure things like, here are the irrigation levels across the farm. Here are the pH levels, the fertilization levels, the temperature, across different areas of the farm. So it's very, very cool things. And then this can lead to a whole bunch of agricultural services. So the yield estimation I mentioned is a huge problem, a really cool thing that we're trying to increase. I talked about precision irrigation, and that can be applied not only to how much you water, but fertilization, pH levels, all of those things. Only put fertilizer on where it's needed versus homogeneously doing it is the precision fertilization, et cetera. So we can apply that to several farming techniques. And then the spread of pests as well is kind of an interesting problem, like being able to predict where they are and where they're going and that sort of thing. So there's all kinds of neat agricultural services that can come out of machine learning processes here. All right, so a little bit more about the drones and kind of how we're doing this from the drone side. I want to talk about kind of the issues that they had along 3 axes. The first one is the drone capabilities, so what the drones can do. And so if you're a farmer, we don't want you to have to be an expert in drone manipulation and flying drones to be able to do this. Like, we wanted to make it like easy for anyone to be able to do. And so they wrote an iOS app that will allow the farmers to do this. And there's 2 different modes it can work in. You can do a point selection mode where you just kind of specify, okay, I want you to follow this path, and it'll just follow a path along those points. Or you can do area selection mode where, again, you select a bunch of areas or a bunch of paths, but that's kind of the boundary that you want, and then it will fly back and forth between there and cover that entire area. And then it does all kinds of things. It can store flight paths. It gives you a checklist. I can show you a little video of it right here. So this is one example of the drone, a farmer. It's a little video of a farmer using this. So first of all, he maps an area on there, and so it's dynamically choosing a route for it. He sets the altitude, so you can choose how high you want the drone to fly over the crops based on what you're doing. You can save off and store that path, so that flight history, so in case you want to fly that drone over the same area again, you can do that. So that's our carnation farm. And then there's a nice checklist so you can remember, oh yeah, did I remove the thing from the gimbal so that the camera can freely move, and did I charge the battery, and all of those types of things. And then it should, hopefully, you hear it? Yeah, that's the drone taking off. You can kind of hear it in the background. So pretty cool stuff. Okay, the next issue with drones is power consumption and battery life. Any of you guys have a drone at home? Okay, cool, a bunch of people. All right, so with drones, you know that even the best drones maybe have like 40 minutes flight time, right? Like the batteries don't last that long. They need to be swapped out fairly frequently. I brought a spare with me, and hopefully this guy is good for the life of the talk. But battery life is a huge issue with drones because they're flying, they're fighting the wind, they're doing all kinds of things to stay in place, and so battery usage can be a huge issue. So there's two main things that we did to combat that. So when we are using an algorithm to develop the path that the drone should fly, we did two main things. The first thing is that the drone actually uses more battery and more power when it is trying to stop and slow itself down and like change directions. Like those things are the most heavy usage of power. And so the way you can obviously figure that out with a little bit of math background is that it makes more sense to have it fly the long direction rather than the short direction, right? So if you have it fly, if you want to reduce the number of times it's stopping and slowing and changing direction, then if you fly the long path, then obviously you only need to change direction 8 times, for example. And if I'm flying the width of it instead of the length, essentially, then I have to change direction 16 times. So they always choose the long path over a given area to optimize the battery usage there. And then the second thing is a yaw algorithm. But to explain that, I first have to explain one little background detail about drones. And that is that there's 2 types of drones. There's this omnidirectional one, which is essentially symmetrical, right? It looks the same from the front or the side. And then there's also directional ones. And this bad boy I have here is a directional one, where you can see it actually looks a little bit different from the side. It kind of, you can have them, you can see it kind of goes down. So there's different amounts of drag, and wind resistance changes whether you're looking at it like this or like this. It's going to give different resistance to the wind. So what they've also developed is a yaw control algorithm. So what that means is that if we have information about the wind and we have the drone's path that it's flying, what we can do is actually change the yaw of the drone to conserve or save energy. So imagine, if the wind was blowing this way and I wanted to accelerate, I can kind of tip like this, tip the drone like this, and then it'll utilize the wind and fly faster. And then when I want to slow down, I kind of go like this, and then that will utilize the drag and increase the drag, the wind resistance, and then it's using less battery and it's using more of the wind. So kind of acting that out in interpretive dance there. But that makes sense, right? Cool? Okay. Awesome. All right, and then the final piece is the networking challenge. So I talked about this at the beginning, that $1,000 per sensor issue that we were having, and how could we fix that? And so if you look at what kind of wireless technologies are available today, we have all kinds of options, everything from like RFID, which you have to be very, very close for it to work, and it's fairly low throughput, to Wi-Fi, where it's kind of got a bigger range, but it really only lasts the range of your house pretty much. If you go out to your across the street, you're going to lose your wireless signal. So all kinds of different things, and then cellular and that sort of thing. But there was nothing that was really good for stretching over these 2,000-acre farms. And so that's where some cool networking research that Ranveer was working on came in. And he was one of the people who was pioneering the idea of television white spaces. So essentially what this means, a little bit of background, if you're dealing with conventional Wi-Fi, that operates typically in about the 5 gigahertz range frequency. And if you're dealing with TV, television signals, as a television station broadcasts out its channel data, that stretches, it's a lower frequency, so it stretches a lot further, right? So you can broadcast much, much, much further to make that work. So the idea is to utilize unused television channels to send data packets and create your own little internet there. All right? So pretty cool, pretty cool stuff. I mean, obviously you have to work with the local government. You can't just go sending stuff over unused television channels willy-nilly. But it's really cool if you look at some of the areas where we've done this in rural areas and in third world countries. There's some really neat opportunities here. And even that, like we're talking about doing this in some of the urban areas in a big city to be able to have, wireless available connectivity available for everyone. Like it's a really, really cool thing. And the idea of just being able to connect to my home internet essentially from 10 miles away is just so exciting to me. Who would not want that? So yay. So we've actually done this and prototyped it in Kenya. So here's one example where we did some work in Kenya, standing this up for a village there. And it was very, and that prototype was pretty successful. And then Ranveer actually went to Ranveer actually went to India about a couple of months ago and was standing up a thing there as well. So pretty cool work there. Okay, so I don't actually have one of the farm drones with me because they're busy doing farming work and we don't have fields here, so their data would not be useful anyway. But what I'm going to try to do, and I'm actually going to do a cheaty way of this, is a really bad demo. And the reason it's going to be really bad is because there is a lot of moving pieces that need to make this work because I'm relying on cellular data. I'm running this over a MiFi, which is kind of crazy. I need GPS to orient the drone, and we're in this beautiful structure with lots of stuff that likes to block signal and all kinds of things. So I did a quick test, and then we also have a little draft going this way. So I did test this beforehand, and it looks like the drone was being unresponsive, and basically it wasn't listening to my controller. So just for safety reasons, because I want Courtney to invite me back, I'm not going to actually fly the drone. But what I'm going to do is a cheesy half thing, because I still really want to show you my demo because I worked really hard on building my facial identification model, so I want you to see it. Okay, so what I'm going to do instead is first I'm going to do this. I'm going to, here's the hacky way we're going to do this. All right, so what I have here is a drone. I'm flying the DJI Maverick Pro right now. And I have an iOS app on here that we wrote. And I'm going to try to connect through AirPlay. Come on. Oh, wow. If all of this works, I will be so impressed, you guys. All right, so so you can see what's coming through on this phone. And then what we're going to do is I'm going to do a cheesy version of this where I'm not actually going to fly the drone just because of safety reasons, because it was being unresponsive. I don't want to get sued later if it goes like that and heads into the audience and the blades get somebody. So what we're going to do instead is a cheesy version of this, I think, just so I do actually show something. I'm going to do, nice dragon drone icon, right? Okay. Now, are you still awake, baby? Here. Let me just make sure everybody is online right now. You should be on the same internet. Yes. As you. Yes. Okay. Then let's try that one more time. And again, I will not be. There's a lot of, why talk about cool research when you could do a demo that relies on 25 billion moving parts to make it actually work, right? Okay, so we're going to try this once and see if it works. Come on, baby, you can do this. Why are you not coming through? All right, let me try this one more time. We're going to do this. We're going to kill this. No, just come on. Whew. All right. Now I'm going to do this and take it out real quick. And then reattach it. And then if it doesn't work, there we go. And now relaunch. Nice, okay. So what I'm going to do instead is a really cheesy thing where instead of actually flying the drone and having it recognize me or whatever, I am going to just hold the drone and point it at me. I know, right? So lame, so lame, so lame. So it does actually work, trust me, when we don't have so much cell signal. So hopefully the lighting is okay, right there. Can we turn the house lights on? Or, it's fine, let's just do it. All right, so 1, 2, and it's not usually trained on something that's so close to me, so let's see how that works. All right, so what's happening now is it is calling the Microsoft Cognitive Services, and yay, it worked, yay! So Drogon would have recognized his Khaleesi, all right? And then I'm going to make him like do flips or something too. Okay, so that is the short version of it. All right, so now let me just close with, I'll show this video. What are we doing after
this area is known as Stewart's Landing, and this is Dancing Crow Farm.
One of the world's problems is yield. How do you double the yield by 2050 to feed the growth of the population in the world? That we recently started, what we want to do is we want to enable data-driven farming. The first goal is to give a real-time view of the farm, the real-time pulse of the farm to the farmer, saying, hey, this is what your farm is doing right now. So how do you even connect these farms to the internet? It's so far remote, the cell carriers have very little incentive to provide connectivity in the farms.
The system that we have deployed here is measuring the soil temperature and moisture, and it's coming from this sensor.
Here what you see is a white spaces device. The idea that we had was a farmer buys a white space router, plug it in the farm, and your entire farm is connected. Now you can connect multiple devices, and connectivity is cheap. So you can actually deploy many more sensors in the farm. You could have a dense deployment of sensors getting real-time view of all the parts of the farm. Not only your soil and moisture data, but this is a high bandwidth connection. You can connect cameras, get real-time views from the farm. So once you have all this data, you could then analyze the data to predict what the future would look like.
I'm actually really looking forward to how the process will change. This last year has been mainly a data gathering, information collecting year for the Microsoft research team. I'm really looking forward to seeing what research they've gathered this year, putting that together with what I think is going to happen next year, and make predictions for what I should plant when and where.
So this is how we could maybe take a step closer to solving world hunger using drones, cutting-edge networking research, IoT, and machine learning. I'm going to skip through. There's a bunch of great resources. I put them into a bit.ly-like thing, a shortened thing. If you want to just go to ak.ms/gen-farm, there's a whole bunch more resources on this project available. And then I have all kinds of answers about like results and such, which I'm happy to share later. Thank you guys so much.